Here we're going to look at the problem, find the values of p for which the series sum n equals 1 to infinity, natural log of n over n to the p converges. So based on the work that we've done so far, it makes sense to look at cases for different values of p. And again, like we did when we looked at the p-test, let's just go ahead and start with the case p is equal to 1. So let's see what happens if we do p is equal to 1. So in the case where p is equal to 1, our sum would be sum n equals 1 to infinity, natural log of n over n. And we're going to use the integral test for this like we've done before. So let's look at the integral from 1 to infinity of natural log of x over x dx. And you guys should make sure that that function natural log of x over x is continuous, positive, and decreasing. And it is. So to evaluate this integral, we'll do a u sub. So if we do u is equal to natural log of x, then our du will be 1 over x dx. So then our integral becomes, remember we want to rewrite it as a limit, so limit b goes to infinity, integral 1 to b, and now we're going to get u du. So this becomes the limit b goes to infinity, integral of u du, so we get 1/2 u squared evaluated from 1 to b. And now we just need to remember that our original integral was in terms of x, so we get limit b goes to infinity, 1/2 natural log of x squared evaluated from b to 1. So we get the limit as b goes to infinity, 1/2 natural log of b squared minus 1/2 natural log of 1 squared. Natural log of 1 is 0, so that term goes away. But as b goes to infinity, natural log of b goes to infinity, so this entire expression goes to infinity, again because this guy goes to infinity, so our improper integral diverges, which means our series diverges for the case when p is equal to 1. So we know that for p is equal to 1, our series diverges. Let's think now about what happens when p is greater than 1. So if p is greater than 1, again I'm going to look at our integral. So integral 1 to infinity, natural log of x over x to the p dx. Again, you need to make sure that this function is continuous, positive, and decreasing. Now here we're not going to be able to do the u sub like we did in the previous case because our du would just be 1 over x, so we're not going to be able to do a u sub, so instead we're going to use integration by parts. So I'll let u be natural log of x, and then dv needs to be the rest of it, so 1 over x to the p dx, or if you prefer, write that as x to the minus p dx, and then my du will be 1 over x dx. So I need something whose derivative is x to the minus p, so remember I'll add 1 to the exponent, so x to the minus p plus 1, and then I need to put a 1 over minus p plus 1, and I think it's easier to see this, rewrite it as 1 over 1 minus p, x to the 1 minus p. So now this gives us, so we'll rewrite as a limit b goes to infinity, so remember the first thing it's u times v, so we're going to get 1 over 1 minus p, natural log x times x to the 1 minus p, and again that's going to be evaluated from 1 to b, and then minus integral v du, so that's going to be minus 1 over 1 minus p, integral 1 to b, so we'll be taking the limit of this entire thing, and I get 1 over x and then x to the 1 minus p, so the 1 over x I'm going to write as x to the minus 1, x to the 1 minus p, and then we have our dx, and I'll just put a line in here so it doesn't start to get too confusing. Okay, so now we need to think about these limits, and again remember we're in the case where p is greater than 1. So in the first part, so we've got our limit b goes to infinity, so I have my 1 over 1 minus p, that's just some number because p is greater than 1. I have my natural log of x, and now because p is greater than 1, I'm going to write an x to the 1 minus p in the numerator. That's the same thing, of course, as an x to the p minus 1 in the denominator if I just flip my the sign of my exponent. And again, this is going from 1 to p, and then I have minus 1 over 1 minus p. Again, now that's just some number. Integral 1 to b. X to the minus 1, x to the 1 minus p, exponents add, and we just get x to the minus p. or 1 over x to the p dx. Now remember, we're only interested in whether this integral converges or diverges. It doesn't really matter what number it's going to go to. So we don't need to redo the work. We've already looked at this second integral. So we have a number in front, but that's not going to change convergence and divergence. So we know that this integral converges for p greater than 1. We already looked at that when we did the p-test, so we don't need to redo that problem. So now we just need to worry about what's going on with this first limit. So again, b is going to infinity. 1 over 1 minus p is just some number, so I don't need to worry about that. I really need to figure out what's happening to the natural log of x over x to the p minus 1 as x goes to infinity. So the limit we need to look at is the following. So I'm not going to put an equal sign now because these expressions aren't equal. I've already said that that second expression, the one circled in red, converges. So I really just need to know what's going on with the limit as b goes to infinity of the natural log of b over b to the p minus 1. Now remember again, we're in the case where p is bigger than 1, which means this is a positive exponent in the bottom, which means as b goes to infinity, this expression is going to infinity over infinity, which means to figure out what this now is equal to, we can use L'Hopital's rule. So L'Hopital's rule tells us that we're going to get the limit as b goes to infinity, 1 over b, so derivative of natural log b is 1 over b, and then derivative of b to the p minus 1 is going to be p minus 1 times b to the p minus 2. And again, now what's happening as b goes to infinity, so now I'm getting, let's just simplify this, so limit b goes to infinity, the 1 over b, I'll just bring that down to my denominator, so I'm getting 1 over p minus 1 b to the p minus 1. So now the exponents have added and I have a p minus 1 as my exponent in the denominator. As b goes to infinity, again remember p is greater than 1, so this is a positive exponent that we have down here in the denominator. So our denominator is going to infinity, which means our entire limit is going to 0. Which means that this first expression is also going to converge. I haven't figured out exactly what it's equal to, but I know that the limit is going to converge, which means my overall integral in the case where p is greater than 1 is going to converge. So far we have diverges for p is 1, converges for p is greater than 1. And now you can see this is a calculation that's very similar to what we did for the p-test. So for the p less than 1 case, I'm going to leave this as an exercise for you to work on. Again, you're going to do the integration by parts, just like I did in the p greater than 1 case, and then your argument is going to be similar to what we did for the p-test example. So when we went through the p-test, go back and look at what we did there. Make sure you can do the case where p is less than 1. You're going to get diverges for p is less than 1. Again, very similar to what we did after you do the integration by parts. Then it's going to look exactly like what we did for the p-test. So going back to answer our question, we're going to say that this series converges if p is greater than or equal to 1, and diverges if p is less than 1.